Hello. In this video we will be discussing a few problems on the concept of potential energy in electrostatics, and we'll be involving this calculation of potential energy in electrostatics while solving some problems which involve mechanical energy conservation, or let's say in general the work energy principles. Now the first problem that we'll discuss is the calculation of the distance of least approach. Calculation of the distance, or rather the calculation of the least distance of approach. Right? I messed up the language there. Calculation of the least distance of approach of an alpha particle approaching a nucleus, a heavy nucleus of charge number Z. So we have an alpha particle which is approaching a nucleus. This is the alpha particle. It's approaching some nucleus, and it has a kinetic energy K alpha. It's approaching a heavy nucleus, and I'm making an assumption that the nucleus is so heavy that the impact by the alpha particle can hardly affect the nucleus in terms of its motion. So the nucleus stays where it is, it hardly moves, there's no change in its position or velocity as the alpha particle strikes this nucleus. Its charge number is Z, so it carries a charge plus ZE. Initially the alpha particle is at infinity, at a very large distance. This is the alpha particle. It carries a kinetic energy K alpha, and its charge number is of course 2, so it carries a charge plus 2E, where E is the familiar electronic charge on an electron. So initially the alpha particle is at a very large distance, that's infinity, and it approaches the nucleus. Now as it approaches the nucleus, what happens is it slows down because of the repulsion from the nucleus. It's slowing down. Eventually what happens is it stops. So it stops here, that means its velocity is 0, and now the distance, the center to center distance, is x naught. After this, as it slows down and stops, after this, because of the repulsion, it moves away. So this x naught is the least distance between the alpha particle and this nucleus, as is done in the famous Rutherford's experiment. Now the closest the alpha particle gets to the nucleus is this distance x naught, and this x naught is what we are calculating in terms of the other given quantities. So it's an interesting calculation, not only from the perspective of this chapter but also from the perspective of nuclear physics, atomic physics. So this was an experiment that was critically important in the development of what's called the Rutherford's model of the atom, and then later also formed the basis, we can say, for Bohr's model of the hydrogen atom. So let's make a calculation. The forces that are acting between the two objects are electrostatic forces which are conservative in nature, and therefore mechanical energy of this system is conserved in this process. Now therefore we can write an equation for the conservation of mechanical energy. And what is essentially happening is at infinity there is no potential energy. So initially when the particle starts off over here, when the particle is starting off here, it has zero potential energy. And the kinetic energy K alpha slowly reduces and is completely converted into potential energy once it reaches here. So the kinetic energy converts completely into potential energy once it reaches here, and then the particle stops and bounces back. So in the position of closest approach is when the distance between them is least. In this position, the kinetic energy will be zero, but there will be some potential energy. Now in the initial position there is no potential energy. In the final position, the potential energy will be given by 1 by 4 pi epsilon naught. Mind you, both charges are positive, so the product of the charges is positive. Potential energy is therefore also positive. So we have ZE times 2E divided by x naught. That's the final potential energy, Q1 Q2 by R. That's the formula we use. The kinetic energy here is zero. The kinetic energy initially was K alpha. Since mechanical energy of the system is conserved, the initial mechanical energy is potential energy plus kinetic energy, and the final mechanical energy is potential. That's 1 by 4 pi epsilon naught ZE times 2E divided by x naught, and finally the kinetic energy is 0. So initial potential energy plus initial kinetic energy is equal to final potential energy plus final kinetic energy, and from here we calculate x naught, and this x naught therefore comes out to be 2Z E square by 4 pi epsilon naught K alpha. So this then is the distance of closest approach, or least distance of approach between the alpha particle and the target nucleus, which in case of Rutherford's experiment was the gold nucleus actually. Now therefore what we can do is we can plug in the values of Z and the known value of kinetic energy of the alpha particle to calculate this distance, and this distance then becomes an upper limit or the maximum possible size of the gold nucleus. So it gives us some sense, some idea of the size of the nucleus. Brilliant experiment conducted more than 100 years ago. Now the second problem we're going to solve will make it a little more interesting. Now here what was happening was one particle was approaching the other, and the second particle was too heavy to start moving in the process. But in the second example, what we will do is we'll take two objects of comparable mass, and which will of course mean that the second object will also start to move. Now have a look here. We have a frictionless horizontal surface here. This is a frictionless horizontal surface, and on this surface we have two objects, two blocks having a mass m each, and they are very, very far apart. They are far apart. This object, this is, let's say, A, and this is B. B is at rest and A starts approaching B with a velocity v0. So A is approaching B with a velocity equal to v0. Initially the blocks are very far apart. They're very, very far apart. So this is at rest, this is moving with velocity v0, and let's introduce an interesting variation. These particles, both of them, have a charge q each, and so there will be some repulsion between them. So they both carry the same kind of charge q. The magnitude of charge is same, the sign of the charge is same, and they're both positive, and there will be some repulsion between them. Both these blocks are free to move on the ground, and as I said initially, very, very far apart. Since they're initially very, very far apart, there will be practically no force between them initially, and as they come closer, there will be some repulsion. Because of this repulsion, what happens is that you have a force to the right on this object and force to the left on this object. As a result, block A slows down and block B speeds up. Again, we are interested in calculating the distance of least or the least distance of approach. So we are calculating the distance or the distance of closest approach. That is, we are calculating the least distance between the two. See, what is going to happen is initially they come closer, and then because of the repulsion they move further apart. So somewhere during this entire process, which we might actually call a collision, the distance between them will be least, and then it will start to increase. We are interested in calculating that least distance of approach. Now, to make this calculation, we have to be a little creative in our thinking. We have to think a little bit out of the box. Whenever we are observing the motion of multiple objects together, it makes sense to use the ideas of relative motion. So what we'll do is we'll imagine that our observer is standing on block B. So we place our observer here. Now let's see if we are this observer and we are looking at A. What we will be seeing is that we will initially observe that A is coming closer and closer to us. I mean, let's say this observer here is me, and I will observe that block A is coming closer and closer to me, and then I'll see that it stops momentarily and then starts moving away. Now it approaches me, comes closer and closer, stops, and then moves away. All the while I'm assuming that I myself am at rest. So I am at rest while I observe A to be moving towards me all the while. So it was moving towards me, then I saw it stop, and then it starts to move away. So when A was closest to me, I observed that it was momentarily at rest. So what that tells me is there was no relative velocity between the two of them when they were closest, and therefore at the moment of closest approach, at the moment of closest approach, both blocks have the same velocity. If they have the same velocity, the relative velocity is 0, and that's why A appears to be at rest when we look at it from B. Now let's take a snapshot of the moment when they are closest to each other. So this is A, this is B, and the distance between them now is x naught. This is the distance of closest approach, and they are both moving with speeds v each at this moment. Now if we consider these two blocks as our system, then for the system of these two blocks there is no external horizontal force. No external horizontal force is there. And since there is no external horizontal force, the linear momentum of the system is conserved in the horizontal direction. So in the horizontal direction, linear momentum is conserved. Write the equation for conservation of linear momentum: 2m times v. The final momentum in this condition is equal to the initial momentum in this condition, which is m times v naught. So m cancels and we have v equal to v naught by 2. So we have this velocity at the moment when the objects are closest to each other. Now, once we are aware of this moment and we are aware that their velocity is v naught by 2 at this moment, what we can do is, now we apply conservation of mechanical energy. If we consider these two as the system, there is no external horizontal force, and in the absence of any external horizontal forces, or in fact in the absence of any external force at all performing any work, we can be sure that the mechanical energy is conserved. There is no internal non-conservative force performing work, there is no external force performing work, there is no release of any kind of internal energy, and in conditions like this, mechanical energy is always conserved. So we now write the equation for conservation of mechanical energy. And what we'll get is initial mechanical energy is purely kinetic energy, because initially the blocks were very far apart, their potential energy was negligible or zero. So initially we only had kinetic energy of this block was at rest. Finally, in this condition, the kinetic energy will be half into 2m, the mass of the entire system, times v square, v being the velocity of the entire system. Now in this case the entire system is moving with the same velocity, v, so half into 2m into v square, kinetic energy, plus potential energy, and potential energy is 1 by 4 pi epsilon naught q1 q2, that's q square by this distance x naught. Now here v can be substituted from here, so we have half m v naught square equals m into, this 2 cancels, m into v square, which is v naught square by 4 plus 1 by 4 pi epsilon naught q square by x naught. We bring this here and we have 1 by 4 mv naught square equals q square by 4 pi epsilon naught x naught. And from here we have our x naught, it equals q square by 4 pi epsilon naught times 1 by 4 m v naught square. And so what we've done here is we've calculated the distance of closest approach. Now there can be a whole lot of questions asked involving the calculation of potential energy and mechanical energy conservation, momentum conservation, etc. I've just demonstrated two problems where I have calculated the distance of closest approach. In some other problems you might be calculating velocities finally, or even initial velocities if final velocities are given, and so on and so forth. There can be an infinite variety of questions, but the ideas, the concepts behind those questions do not change. They remain the same. Hopefully this demonstration of problem solving will clarify for you the process of problem solving when, as a part of mechanical energy, you're also considering electrostatic potential energy. Thanks very much for watching. The next video, of course, is going to be very, very exciting. It's going to be about the behavior of conductors, which is a difficult topic, but at the same time very, very interesting topic as well. Thank you very much for watching the video. Please keep sharing and liking these videos if you're enjoying them, and of course do not forget to subscribe if you haven't already done this. Thanks a lot.